Assalamu alaikum, gentlemen. Good morning. This is Bismillah ar-Rahman ar-Rahim. This is lecture number 13. We will continue today with the network theorems, part 2. Last week you have learned how to apply superposition theorems to solve electrical circuits. Today we will learn the concepts of Thevenin's theorem and how to apply this theorem to reduce complex networks into simpler form, to analyze circuits and design electrical circuits. And also we will learn about the concept of maximum power transfer and how to apply the maximum power transfer theorem to electrical circuits. So we will be using Robert Boyle's book. So you can find the theorems, Thevenin's theorems in section 9.3, and maximum power transfer theorem in section 9.5. So let's start with Thevenin's theorem. Thevenin's theorem is probably one of the most interesting as it allows reduction of complex network and to a simpler form in order to facilitate the analysis and the design of electrical circuits. In general, the theorem can be used to do the following: analyze the complex networks, reduce the number of components required to establish the same characteristics at the output terminals, A and B, as you can see here. Investigate the effect of changing a particular component on the behavior of the network without having to analyze the entire network after each change. All these three areas of applications will be demonstrated through the examples that we will go through during this lecture. To explain this, let's see this figure. Let's consider a complex network as shown here. This complex network might include more than one source, many voltage and current sources, resistors connected into parallel, into series. So let's imagine a complex network with different loops, a certain number of nodes, and we are interested to see how it will be it can be represented, seen from two terminals, A and B. So the problem is how to simplify this complex network into a simpler form. What is this simpler form? It includes a voltage power supply, E Thevenin, and a resistor in series, R Thevenin. So any two-terminal DC network can be replaced by an equivalent circuit consisting only of one voltage source, E Thevenin, and one series resistor, R Thevenin. So this is the concept, is to reduce a complex network into a simple network, and this will facilitate the analysis and the design of electrical circuits. Through the example, you will understand very well how to apply this Thevenin's theorem. So to apply this Thevenin's theorem, of course, before we have to ask a question, how can you determine the proper value of the Thevenin's voltage and resistance? So as you can see here, we have to determine R Thevenin and E Thevenin. Okay, how to determine R Thevenin and E Thevenin? In general, finding the Thevenin resistance value is quite direct and easy, because we have learned in previous lectures how to determine the total resistance seen from two terminals. Finding the Thevenin voltage may require more work, but you have learned techniques in previous weeks like voltage divider law, Ohm's law, current divider law, Kirchhoff voltage law, Kirchhoff current law, superposition theorem, mesh analysis method, and nodal analysis method. All these techniques will help you to determine the E Thevenin or the Thevenin voltage. There are series of steps. So to help you understand the procedure, we will show you through example the steps that you should follow to determine R Thevenin and E Thevenin. Okay. You have to learn how to apply these steps, because in some simple circuits it might seem that some steps may seem trivial at first. Then they become quite important when the network becomes complex. So please, gentlemen, you have to apply and follow the steps that we are going to show you. So let's see step number 1. First of all, we have to remove the portion of the network where the Thevenin equivalent circuit is to be determined. This requires that the load resistor RL be temporarily removed from the network. Let's see. Let's consider this circuit. We would like to determine the Thevenin equivalent circuit of the part highlighted in blue. So as you can see here, we have one voltage source with 2 resistors, R1, R2. And here we have RL, R load, connected to terminals A and B. So I would like to see what is the equivalent, to determine the Thevenin equivalent circuit of the portion which is highlighted in blue. So first of all, we have to remove RL from the circuit. As shown here, we have removed RL from the circuit. So this is step number 1. Step number 2, we have to mark the terminals A and B. Okay, so we have to mark the terminals A and B. We have here 2 terminals. We have to mark these 2 terminals. Here we put A and B. The third step is to calculate the Thevenin resistor, R Thevenin. How we calculate the R Thevenin? First of all, we have to make sure that all the sources are replaced. If it is voltage source, it should be replaced by a short circuit, and if it is a current source, it should be replaced by an open circuit. So here, how many sources we have? We have only one source. What is this? The type of the source is voltage source, so we have to replace it by a short circuit. If there is a current source, we replace it by an open circuit. So here we have to replace it by a short circuit. So here, to calculate R Thevenin, we have to first set all the sources to 0. Voltage sources are replaced by a short circuit, and current sources are replaced by open circuits. And then finding the resultant resistance between the 2 market terminals. So here we have the 2 market terminals, A and B. So we have to see from here and determine the resultant resistance seen from AB. So how we calculate R Thevenin here? We can see that R1 is in parallel with R2. So R Thevenin is R1 in parallel with R2 equals 2 ohms. It is important to note that if the internal resistance of the voltage or current sources is included, if, for example, here we have the voltage source, it has its internal resistance, we should not remove it. We should only replace the voltage source by a short circuit and keep the internal resistance here, if there is one. Okay, so here, if the internal resistance of the voltage and or current source is included in the original network, it must remain when the sources are set to 0. So here there is no internal resistance. That's why we have only one ideal source here, and we replace it just by a short circuit. So here we have done step number 3. We have calculated our Thevenin by making 0 all the sources in the circuit. Here, only one source. We replace it by a short circuit. Now let's go to step 4. Calculate E Thevenin. How to calculate E Thevenin? Let's first return back the sources that we have removed or we have made 0 in the previous circuit. So all the sources are returned back. Here we have to calculate the voltage across AB. Okay, as you can observe here, E Thevenin is the voltage across R2. So E Thevenin is equal to VR2. So how to determine this voltage across R2? It's simple. We just have to apply the voltage divider rule to determine VR2. So VR2, which is E Thevenin, equals R2 divided by R2 plus R1 times E1. It is equal to 6 volts. So here we have obtained the E Thevenin using the voltage divider rule. Okay, so once we have R Thevenin and E Thevenin, we can now draw the circuit and replace all the highlighted, the portion which is highlighted in blue, we replace it by its Thevenin equivalent circuit. So what we have here, we have to come to replace it by its equivalent Thevenin equivalent circuit. So this circuit is now replaced by its Thevenin equivalent circuit with E Thevenin equals 6 volts, with R Thevenin equals 2 ohms. And we connect again the resistor RL that we have removed previously. So as you can see, we have reduced the complex circuit into a simple circuit that we can analyze, we can study, we can calculate currents, voltage easily across the load resistance RL. So here, step number 5 is to draw the Thevenin equivalent circuit with the portion of the circuit previously removed between the terminals A and B of the equivalent circuit. This step is indicated by the placement of the resistor RL, okay, between the terminals of the Thevenin equivalent circuit. Now we are ready to investigate the effect of varying or changing RL on the current going through RL. So here, investigate the effect of changing RL on the current IL. You know that IL is E Thevenin divided by the sum of the two resistors, R Thevenin plus RL. So here IL is equal to E Thevenin divided by R Thevenin plus RL. If we change the value of RL, let's assume that we have a constant voltage. Of course, E Thevenin should be not changed, only RL. We are going to see the effect of changing RL on the current going into the load. So we change RL. RL equals 2. We can calculate IL equals 1.5 amps. For RL equals 10 ohms, IL is equal to 0.5 amps. And for RL equals 100 ohms, IL is found to be 0.06 amp. Here it is very interesting to note that without transforming the circuit into its Thevenin equivalent circuit, studying the effect of changing RL on the current IL will be a tedious work, will require to recalculate each time, solve the circuit. By changing RL, we have to solve 3 times, 3 circuits, and this will be time consuming. So here we have to note that if Thevenin theorems were unavailable, if we don't apply Thevenin's theorem, each change of RL would require that the entire network be re-examined to find the new value of IL. So this refers to the application number 3 in slide 5. As you know, here the application number 3 states that investigate the effect of changing a particular component on the behavior of the network without having to analyze the entire network after each change. So this is the advantage of converting the network into its Thevenin equivalent circuit, because it will facilitate the study later on. Okay, so this is the concept and the procedure to be followed using example. I choose to give you the procedure, to explain the procedure through example. Okay, so we have the different steps here. Step number 1, we remove RL and we mark the terminals. Step number 2. Step number 3, we make all the sources to 0. Here we have only one source, we replace it by a short circuit. Then we calculate the R Thevenin seen from AB using the technique that you have learned in previous classes. Then we return back all the sources and we calculate the E Thevenin, which is the voltage across AB, with RL removed also, of course. So here VAB is E Thevenin, which is found to be the voltage across R2 in this particular example. So we have to calculate VR2, which is equal to E Thevenin using the voltage divider rule. It is 6 volts. Once we get E Thevenin and R Thevenin, we replace all this part by its Thevenin equivalent circuit, and then we can return back, reconnect the R load and study the effect of changing R load on the current going into the load. Okay, this is a very good example to explain the procedure and the concept of the Thevenin's theorem. Let's go through examples now. Okay, let's consider this circuit, which is in figure 9.32. For this circuit, find the Thevenin equivalent circuit for the network in the shaded area, okay, as shown here. Okay, here we have R3, and we would like to replace this portion of the network by its Thevenin equivalent circuit. So first of all, we have to go step by step. We have to apply step 1 and 2. What is step 1? Is to remove R3 first. So we have removed R3. Then we have to mark the terminals A and B. So here we have step 1 and step 2 done, because we have removed R3 and we have marked the terminals A and B. Now, the third step is to make all the sources 0. Okay, here what we have a current source. So what does it mean making the current source 0? Is to replace it by an open circuit. So here for step 3, as you can see in figure 9.34, we have replaced the current source by an open circuit. And then we will see from AB and we calculate R Thevenin. So what we see here, this is an open circuit. It will be removed. Okay, so we will find that R2 is in series with R1. Okay, here when we remove the current source, here R2 will be in series with R1. So what is R Thevenin? Is R1 plus R2 equals 6 ohms. So step 3 done. Now let's go to step 4. We return back the current source, and then we calculate the voltage across AB, which is E Thevenin. As you can see here, it's an open circuit here. Okay, so there's no current. I equals 0. What does it mean? The voltage across R2 is 0, because based on Ohm's law, V2 equals I times R2. Since I equals 0, V2 equals 0. So the point A is found to be the point here, the same. This point A is the same point here. This is the terminal of R1. And this point B is this terminal, because there is no current. The voltage drop is 0 here. So what is E Thevenin? E Thevenin is found to be VR1, the voltage across R1. Okay, so since there is no current here, all the current will go into the resistor R1. So here R1 will have I going through, which is equal to 12 amp. Okay, so what is the voltage VR1 here? VR1 is equal to I1 R1 is equal to E Thevenin is equal to 12 times 4, 48 volts. So here we have found E Thevenin is equal to 48 volts. What about R Thevenin? 6 ohms. So now we can replace this portion of the circuit by its Thevenin equivalent circuit, which consists of one voltage source, E Thevenin equals 48 volts, with in series with one resistor, R Thevenin equals 6 ohms. So now we have the Thevenin equivalent circuit of all this portion. Now we can return back and connect again R3, 7 ohms. We can determine now the current going into R3, calculate the voltage across R3, calculate the power dissipated by R3, etc., using the techniques that you have learned in previous weeks. So you see, gentlemen, how we apply the procedure, and step by step we convert and we simplify a complex circuit into its Thevenin equivalent circuit, which is very simple circuit, just one power voltage supply in series with one single resistor. Okay, again we will do another example. For figure 9.37, as shown here, what we are interested in is to replace all the the portion which is highlighted in blue by its Thevenin equivalent circuit. What you can see here is R4. So R4 should be removed from the circuit, and we should see from AB what is the equivalent, the Thevenin equivalent circuit. Okay, so we will try to obtain the Thevenin equivalent circuit of the portion which is highlighted in blue. Okay, so the first step is to remove R4 as shown in figure 938. We have removed R4. The second step is to label the terminals A and B, already labeled A and B. So we have removed R4 and we have marked the terminals. Now we go to step number 3. What step number 3 says? We have to make all the sources equal 0. And we have to replace the voltage sources by a short circuit and the current sources by an open circuit. Here in the circuit we have only one voltage source, so we have to replace it by a short circuit. This is shown in this figure. We have replaced it by a short circuit. And we have to see from AB and try to find the equivalent resistor. So what you observe here, that R3 is found to be short-circuited. So what do you think? If we short-circuit a resistor, it means that we removed it from the circuit. So here the resistor will be the equivalent resistor of a short circuit in parallel with the resistor is 0. So R3 with R here it is 0. R3 in parallel with 0 gives 0. So what we will find that R Thevenin is the resultant of R1 in parallel with R2. So this is the circuit which is redrawn. Okay, we have R1 in parallel with R2. Why? Because R3 has been removed because it was short circuit. As you have learned in previous lectures, when we short circuit the resistor, as if we remove it. Okay, if the voltage is 0, means that the current is 0. It means that this as if it is an open circuit. So we have R2 in parallel with R1. If we see from AB, we will see R1 in parallel with R2. By applying the rule of parallel resistance, we find R Thevenin equals 2.5 4 ohms. So step 3 done. Next step is to determine V Thevenin. We return back the voltage source. Having AB, the resistor R4 removed, we will try to find the voltage across AB. So what is the voltage across AB? Is E Thevenin. What is AB? Is the voltage across VAB is the voltage across R1. So we have to determine the voltage across R1, which is E Thevenin. Okay, by applying the techniques that you have learned. So what we have here, we have an open circuit, of course. This is open circuit. Okay, so we have a voltage source E1 in parallel with R2 in series with R1. And we are interested to determine the voltage across R1. It's very simple here. We will apply the voltage divider rule to determine the voltage across R1, as simple as that. So what is the voltage across R1? It is R1 divided by R1 plus R2 times E1. Here E1 is in parallel with R3. It doesn't interfere. R3 is in parallel with E1. But we are interested to determine the voltage across R1. So R1 and R2 are found to be in parallel with the voltage source. So the voltage source, the voltage across R1 plus R2 is found to be 8 volts. So we can determine using the voltage divider rule the voltage across R1, which is equal to 4.8 volts. You see here the polarity of E1, the polarity here. So here we should expect that the current comes from here, and the voltage E Thevenin will have this polarity. E Thevenin will be having this polarity. So the voltage source E Thevenin will have positive down and negative terminal up side. So here, what is the Thevenin equivalent circuit of all this part? It is as simple as this highlighted portion. It is E Thevenin plus minus, we do respect the polarity that we have found, in series with R Thevenin, which is equal to 2.4 ohms. Okay, so in step 5, we will replace the circuit, the portion of the circuit highlighted in blue by its Thevenin equivalent circuit, and then connect R4 again. And now we are ready to analyze the power, the voltage, the current going into R4. Imagine R4 is a load that where we are interested to calculate the current, the voltage, the power dissipated by R4. And we are interested to see the effect of changing R4 on the performance of the load. So all this is simplified thanks to Thevenin's theorem, application of Thevenin's theorem. So here, the importance is to determine the amplitude of E Thevenin and also determine the polarity, of course. Here we have, it's very important to know where is the plus, where is the minus. As you can see here, the current coming from this side, so the plus is in this side, in this terminal, and this terminal is minus. Okay, let's go to another example, 9.9. Let's see this circuit. It seems very complicated, and we are interested to calculate, for example, the current, the voltage across RL. So what is the procedure here? And we have to apply the Thevenin theorem to replace whatever is highlighted in blue by its Thevenin equivalent circuit, and then connect again RL and calculate the current, the voltage, whatever in RL. So step number 1 is to remove RL. Done. Step number 2 is to label the two terminals, A and B, already done. So step number 1 and 2 is done here. We have removed RL and we have labeled the two terminals. Now, let's go to step number 3. We have to reduce all the sources to zero. Here we have only one voltage source. We have to replace it by a short circuit, as it is shown in figure 4.9.45. So we have replaced the power voltage supply by a short circuit. Okay, and now we have to see from AB what is the resultant resistance. As you can see, gentlemen, here you have to see the circuit in a different way. You can see that R1 and R3 are in parallel. Why? Because they have a common point here, and also because we have short circuit the power supply, they have this point and this point. The two terminals are connected together. So they are connected in parallel because they have their two terminals connected together. So this terminals for R1 and R3 are connected together, while this terminal of R1 and this terminal of R3 are also connected together because we have short-circuited the source. The same happened for R2 and R4. So R1 and R3 are in parallel. R3 and R2 are also found in parallel now. Once we short circuit the power supply, we have made R3 and R1 in parallel, and R4 and R2 in parallel. All together they are connected to this point, the ground. So if we see from A and B, we will find R3 in parallel with R1 in parallel with R2 in parallel with R4. So what is R Thevenin? Is RAB equals R1 in parallel with R3 plus, sorry, it is in series. They are in series. Here it is just a point, okay? So it is R1 in parallel with R3 plus R2 in parallel with R4. This is a very simple point. The ground is a simple point that they are in series. This is the block, parallel block R1, R3 is in series with the parallel block R4 and R2. So R Thevenin is equal to RAB equals R1 in parallel with R3 plus R2 in parallel with R4. It is equal to 5 ohms. So we have found we have determined the R Thevenin. Let's go to step number 4. We will return back the voltage source, and we will try to calculate the voltage across AB, which is E Thevenin. Okay, so E Thevenin, if we apply the Kirchhoff voltage law in this loop, we can determine E Thevenin, because here by applying the KVL in this loop, we have plus E Thevenin plus E Thevenin plus V1 minus V2 equals 0. Okay, so what if we find V1? V1, what is V1? We can obtain V1 by applying the voltage divider rule. It is R1 divided by R1 plus R3 times E. It is 48 volts. What about V2? Again, we apply the voltage divider rule. We know the voltage across R2 plus R4. It is for 72 volts. So we can apply voltage divider rule here to determine the voltage across R2 is equal to R2 times E divided by R2 plus R4 equals 54 volts. So once we have V1 and V2, we can determine E Thevenin easily. So E Thevenin is equal to V2 minus V1 is equal to 54 minus 48 equals 6 volts. So here, after completing step 4, we have E Thevenin obtained 6 volts and also R Thevenin 5 ohms. So we can replace all this portion of the circuit by its Thevenin equivalent circuit. Okay, here as you can see here, E Thevenin, the positive terminal is at B, and the negative terminal is at A. Okay, because here we found the result positive, and here the direction or the polarity of E Thevenin that we have put here is as it is shown here, positive at terminal A, B, and the negative at terminal A. So here the polarity is very important, gentlemen. Okay, so plus will be at terminal B, and the minus will be at the terminal A side. So here we have replaced the circuit by its Thevenin equivalent circuit, 6 volts in series with 5 ohms, and we have connected again RL, and now we are ready to determine the current in the load, voltage across the load, power dissipated in the load, etc. Another example, gentlemen. Let's consider figure 9.48 as shown here. We have here resistors which are connected as shown here. We have here E1 minus 6 volts and E2 equals plus 10 volts. And here we have the resistance RL which is connected to ground. What we are interested in is to simplify this complex network into a Thevenin equivalent circuit. As you can see here, E1 minus 6 means that from this point to ground there is a power supply which is negative. Polarity at this point minus, and the polarity plus, polarity is at the ground. So we have replaced, we have drawn this circuit in a different way. We have completed here minus 6 volt, it means we have a power supply from this point minus to ground, plus terminal is at the ground, and E1 is 6 volts. The same for the resistor R2, then from this point to ground there is a power supply. What is this power supply? It is plus at this point and minus at the ground terminal. So here we have E2 10 volts with this polarity, and E1 6 volts with this polarity, all connected to ground. So we have redrawn this circuit in a circuit that you can easily visualize and study. Okay, and we have removed RL. So step number 1, we have removed RL. We have redrawn the circuit in a form that you can see clearly. Okay, and we have marked the terminals A and B. So step 1 and 2 done. Step number 3, we have to make all the sources to 0. Here we have 2 voltage sources. We have to make them 0. So we have to replace each one by a short circuit. This is what we have done this here in this figure. We have replaced E1 by a short circuit, and we have replaced E2 by a short circuit. Then we have to calculate the Thevenin resistance, R Thevenin, seen from AB. So what we can see here, we can see that we have R4 in series with a parallel block here, which is R1 in parallel with R2 in parallel with R3. So we can calculate easily R Thevenin using the technique that you have learned. So it is R4 plus R1 in parallel with R2 in parallel with R3. You know the technique, that's why I'm not showing you the way we calculate. It is 2 kilo ohms, you can check. So R Thevenin is equal to 2 kilo ohms. Next step, step 4. We return back all the voltage sources. Then we, of course, we keep the terminals AB open. We do not connect RL yet. And we have to calculate the voltage, the Thevenin voltage. E Thevenin is the voltage across AB. So E Thevenin is VAB. Okay, is equal to VR 3. Why? Because since it is an open circuit here, there is no current in R4. It means the voltage across R4 is 0. So the voltage drop across R4 is 0. So A is at this point, same. B is the ground also. So what is E Thevenin? Is the voltage across R3. Here we have to calculate E Thevenin with the polarity, with the sign of the result will give us the polarity of the power supply or the voltage supply that you have to use to represent the Thevenin equivalent circuit. So let's apply the nodal analysis technique that you have learned in previous weeks. So let's identify the different nodes. We have 2 nodes. This node, which is chosen to be the reference, and we have the node V here. This point and this point are known because here we have E1, E2 known. So we will apply the nodal analysis technique. So let's write the current, the Kirchhoff current law, apply the Kirchhoff current law to node at node V. So to do this, we have to consider that all the currents are leaving the node, except those currents which are determined by the current sources. Here we don't have any current source connected. So we consider that all the currents are leaving the node. And then we apply the current Kirchhoff law. So what is this current? Is the voltage at this point minus the voltage at this point divided by R1. What is this current in branch R2? Is the voltage V minus this voltage divided by R2. And what is this current? Is V minus 0 divided by R3. So the sum of all the voltages, the currents leaving the node, is equal to 0. Here we don't have current source. So here, the current in branch R1 is V minus E1. Why minus? Because here at this point, it is minus E1. Here we have the negative polarity, negative polarity of E1. So it is V minus E1 divided by R1 plus V minus E2 divided by R2 plus V minus 0 divided by R3 equals 0. We replace these by the values, okay, and we will get this equation. Of course, if you saw replace these parameters by their values, you will find we will group all the terms that multiplies V, which is 1 over R1, 1 over R2, 1 over R3, which is 1 over 800 ohms plus 1 over 4,000 ohms plus 1 over 6,000 ohms times V, and minus E1 divided by R1 minus E2 divided by R2. If we calculate them, we find that it is from the other side will go and will become minus 1 divided by 200. So, of course, we can determine V. V equals minus 600 divided by 200 equals minus 3 volts. What does it mean, the sign, the negative sign? It means that VB is greater than VA, because here we have calculated VAB. So VB is greater than VA. It means that the positive terminal of the voltage source, E Thevenin, is at B, and the negative terminal is at A side. So step number 5, we have replaced this highlighted portion of the circuit by its Thevenin equivalent circuit. And we connect again RL, and now we are ready to calculate current, voltage, power in RL and study the circuit. You see the effectiveness of applying Thevenin's theorem in simplifying the circuit. Here we have 2 loops, complicated circuit that we have simplified into replaced by a very simple circuit. The characteristics of this circuit is similar to the circuit that we have in the original figure. the same. It behaves the same, but it is in a simple form. This simple form will facilitate the analysis and the design of electrical circuit, as seen here. With the simple form we have, it will be much easier to analyze and calculate the current in the load. Okay, this completes the Thevenin's theorem. Now we will go to the maximum power transfer theorem. Let's consider that we have a complex circuit that we have reduced to a Thevenin equivalent circuit. And now we have a resistor RL, a load, which is connected to this circuit. And we are interested to see what will be the effect of changing RL on the power that will be absorbed by RL, because we want to know how much power we can extract from this circuit or from this network, and we want to see what maximum power we can extract from this network. Okay, we have observed that by measuring the voltage and the current here in the load, and by varying the load, we vary the load from 0 to infinity to open circuit, from 0 to open circuit. We found that the power which will be dissipated in this load will have this shape. As you know that if RL equals 0, the voltage across will be 0, and also the power dissipated or absorbed by the load will be 0. If the resistor RL is set to very high values, infinity it means open circuit, there will be no current here. If RL is set to very high values, I will go to 0. So the power also will go to 0. So this point and here, this point, it's not shown, but if we continue, we will go to R equals infinity. We will get the power will decrease until it goes to 0. Okay? But at a certain point, the power will change direction. Here, the power is increasing, and from this point, the power starts decreasing. It means that this point is the maximum, is the point that corresponds to the maximum power that we can extract from this network. This, we call it Pmax. Okay, this is the point that corresponds to the maximum power transfer, that the maximum power that it can be transferred from the network to the load. When this point will occur? This point will occur when RL is adjusted to be equal to R Thevenin. At the point where RL is equal to R Thevenin, we observe that the power is maximum, at its maximum value. Before, the power increase until that maximum value. After that, it will decrease until it reaches 0, as explained here. So, as you can see here, we know the behavior of the power dissipated or absorbed by the load when we change the RL. And we have observed that when we set RL equals to R Thevenin, we will get the maximum power transferred to the load. So when designing a circuit, it is often important to be able to answer one of the following questions. What load should be applied to the system to ensure that the load is receiving maximum power from the system? I have answered this question. My question is, how can we set RL to get the maximum power absorbed or transferred from the network to this load? Because we are interested to have the maximum power. The maximum power means the maximum heating, it's maximum whatever lighting, it's okay. For a particular load, what condition should be imposed on the source to ensure that it will deliver the maximum power available? Let's say we have this network, and this network is capable to deliver this power, maximum power. This network is given, is there, is ready to deliver a certain maximum power, with condition that we adjust RL equals R Thevenin. But unfortunately, we did not adjust RL. We put RL much less than R Thevenin. What power we should expect to extract here? We will be extracting power which is much less than the capability of the system, of the network to deliver power. The network is capable to deliver Pmax while we have adjusted RL here. So it's a very important question, because here we would like to know what resistor value we should adjust to get the maximum, to extract the maximum power from the network. So we have to know, have an idea about R Thevenin. And if we select RL close to R Thevenin, we will be happy, because as given here, if a design calls for a load of 100, for example, a load of 100, to ensure that the load receives maximum power, using a resistor of 1 or 1 kilo results in a power transfer that is much less than the maximum. So here, this is a very good example. If the maximum, the resistor that will correspond to maximum power is 100, but we did not connect 100. We connected only 1 ohm or 1 kilo ohm. So working here and working here doesn't give us maximum power transfer. So it will be giving us power which is much less than the power, maximum power that can be transferred. But if we select resistance or load of 82 ohms or 120 ohms, we will be here. We will be here in this point. This, for example, for 82 ohms, and here for 180 ohms. So we will be close. We will be not far away from the power maximum that can be transferred to the load. Okay, let's do an experiment. Let's assume we have done an experiment here. We have considered this circuit. We have this network, which has its E Thevenin calculated like we have seen in previous sections, and R Thevenin determined, 60 volt, and R Thevenin equals 99 ohms. And we have connected a variable resistor here that will simulate the load, variable load. Okay, we have measured the current IL. We have measured the voltage across RL. Okay, so for RL equals 0.1, we have measured 6.6 amp and 0.66 volts, and the power dissipated or absorbed is 4.35. So we increased the load until we reached this point at 9 ohms. When we adjusted RL at 9 ohms, what we observed that we have measured 3.33 amps and 30 volts. Okay, so we have calculated the power, which is 100 watts. But above this value, above 9 ohms, we observe that the power starts going down, starts decreasing. Why? Because we are in this region. In this region, the power decreases. In this region, the power increases. Here, the power decreases. Where is the maximum? It corresponds to RL equals R Thevenin. So it can show you clearly that using this experiment, we can identify which power is maximum and at which resistance value it will have, we will have maximum power transfer. And we have observed that 9 ohms, it corresponds to R Thevenin. So the condition to have maximum power transfer is to set RL equals R Thevenin. Now, we have understood that to get the maximum power transfer, RL should be set to R Thevenin. So what is this maximum power? How to calculate? We use the techniques that you have learned. So first of all, we calculate IL. It is equal to E Thevenin divided by R total, R Thevenin plus RL. It is equal to E Thevenin divided by 2 R Thevenin. PL equals I all squared times R all. Here it is E Thevenin divided by 2R Thevenin squared times R Thevenin. Here we have R Thevenin in the numerator and we have R Thevenin squared in the denominator. We can simplify by R Thevenin. So we will have E Thevenin squared times divided by 4 R Thevenin. So this is the maximum power that can be extracted by the circuit when we connect an RL, a resistor RL, which is equal to R Thevenin. So the capability of the circuit can be the maximum power that the circuit can deliver is PL max. It will not occur at any value of RL. It will occur only at RL equals R Thevenin. When we adjust RL to R Thevenin, we will get the maximum power. We will extract the maximum power from the network. Okay, let's see an example. Given the network in figure below, find the value of RL for maximum power to the load. So we have E Thevenin 6 volts, R Thevenin 2 ohms. I'm interested to determine the value of RL that makes the maximum power transfer to the load. So as we have learned, RL should be equal to ohms. So RL equals R Thevenin equals 2 ohms. And the maximum power transferred to the load is E Thevenin squared divided by 4 times R Thevenin is equal to 4.5 watts. So the maximum power that can be transferred to the load is 4.5 when the load is adjusted and is set to be equal to R Thevenin. This is example 1. The other example, let's consider this circuit. This is RL. And we are interested to determine the value of RL that guarantee a maximum power transfer from this network. So we have RL, which is connected to this network, and we want to find RL that makes the maximum power transfer to RL from this network. So what is the procedure, gentlemen? Is first to determine the Thevenin equivalent circuit seen from AB. So the Thevenin equivalent circuit of this portion of the circuit of the network, this network, should be determined first. And then we connect RL and we set RL equals to R Thevenin. So we have to determine R Thevenin seen from AB and V Thevenin and E Thevenin, and then calculate RL and P max. So we will follow the steps that we have learned in previous sections. First of all, we remove RL. Then we will make all the sources equal 0. Here we have to make this source open circuit. So what we have, R Thevenin equals R1 in series with R2, in series with R3. So what is R1? R Thevenin is equal R1 plus R2 plus R3. So here, by replacing all the sources to 0, here we have a source, voltage source, we replace it by short circuit, and here we have a current source, we replace it by an open circuit. So sorry, here there is short circuit and this is open circuit. So what is the resistor? The resistance seen from AB, it is R1 plus R2 plus R3. It is 15 ohms. Now we return back all the sources. We return back and keeping AB open, and we determine the voltage across AB. So as you can see here, since it is an open circuit, here the voltage is 0. There is no voltage drop across. So here we have the voltage source. Here we have the current source in parallel with the R2. So we have to calculate the voltage across. So V1 equals V3. V1 equals V3 equals 0 because here there is no current and here there is no current. So this is the voltage drop across R3 is 0, and the voltage drop across R1 is 0. And V2 is equal to IR2, because here there is no current and here there is no current. So the only current, the total current of the source will go through R2. So what is V2? Equals 60 volts. Then we apply the current, the voltage Kirchhoff law. Okay, here the voltage Kirchhoff law. What is VAB? Is found to be, here we have minus V2 minus E plus E Thevenin equals 0. Here there is drop 0 voltage, the voltage drop is 0, and here the voltage drop is 0. So by applying the Kirchhoff voltage law, we determine E Thevenin. E Thevenin is found to be 128 volts. R Thevenin is 15 ohms. So here we have R Thevenin, so RR should be set to 15 ohms. And the maximum power that we can extract from this circuit is given by this formula, E Thevenin squared divided by 4 R Thevenin. It is 273.07 watts. So you can see here we have applied the Thevenin theorem to simplify the circuit, to determine R Thevenin and V Thevenin, and also to calculate the maximum power that can be transferred to the load. And the load we have to set to get this maximum power transfer. So we have done analysis plus design. So we have designed the load, we have selected the load in order to get the maximum power transfer. You can see how this technique, or how these theorems help us to analyze the circuit in an easy way. Okay, so you are ready now for the homework. So we have problem number 1. For this circuit, we have to calculate the Thevenin equivalent circuit, and then we determine the effect of changing R on the current going into the resistor R. So first of all, you have to remove this. Go step by step, gentlemen. Apply the steps that you have learned today. Okay, and then you calculate the current for R equals 2 ohms, 30 ohms, and 100 ohms. You have here 4 different circuits. Here we have this R, okay, and we are interested to determine the equivalent Thevenin equivalent circuit for this network, okay, and then once you determine the Thevenin equivalent circuit, you reconnect R, and then you calculate the current for different values of R, 10 ohms, 50 ohms, and 100 ohms. You repeat it for all these circuits. Now, also you have to determine the Thevenin equivalent circuit for these 2 circuits. And here you have to refer to problem number 2. So problem number 2, once you determine the Thevenin equivalent circuits of this, you do a design problem, and you select R in such a way you get the maximum power transferred from the network to R. So here, use the results found in problem 2 to find the value of R for maximum power to R, and to determine the maximum power to R. Okay, so good luck, gentlemen, and make sure that you go through all the problems, go through all the examples, and go through all the problems, and try your best to solve the problems before you see any answer coming from the teacher. Thank you, gentlemen, and wish you all the best. Thank you.